Okay, let's try number 4. I think I can do it all. I don't have to move it to more room. I should have enough room to do this. This tells us to show the mechanism for the formation of the hemiacetal. And we've given you the product. Remember, a hemiacetal is a carbon that's bonded to 2 oxygens, but one of the oxygens still has a proton on it and is an OH. The other is an oxygen of an ether functionality. So this is a hemiacetal. We've gotten the product. We just want to know, how do we get from here to here? Notice that we have a 1, 2, 3, 4, 5, 6-membered ring. What we have to realize is that this is the carbonyl carbon from the reactants. So if that's carbon 1, 2, 3, 4, 5, 6, we can get a 6-membered ring by this attacking that carbonyl. Now it's under acidic conditions, and what do we do under acidic conditions? We always protonate. So let's go ahead, let's expand this and put our lone pairs of electrons on our oxygen. And the first step, when we see that proton above the arrow, is we're just going to protonate. So let me go ahead and put my H plus here as well. I'm going to protonate it. That's all we're going to do. Now I'm going to cheat, and I'm going to take this, copy it, and I'm going to move down here. Acid-base reactions are, of course, oops. Okay, now let's erase that. And we have a proton, so let's erase both those. We'll put a positive charge on that oxygen. Okay, so now we've protonated the carbonyl oxygen, and when we do that, we've made this thing very electrophilic. So let's make it blue. Electrophiles are blue. Where's our nucleophile? We don't have anything else here. We don't know if we're in water. We may be. We're making it a hemiacetal. So let's go ahead and use the lone pair of electrons here. Let's use this OH group as our electrophile. I'm sorry, our nucleophile. Okay, so now we're just going to attack our electrophile with the nucleophile. And in fact, we're very close. Just going to go over like this, go over to here. Okay, and I've made, let me get my laser, I've made a 1, 2, 3, 4, 5, 6-membered ring where I have an oxygen bonded to this carbon, and that carbon's going to have an O and an H bonded to it, just like that. So in fact, what I'm going to do is draw my 6-membered ring with an OH. There's also a methyl group right here, so I have to put a methyl group there. There's my methyl group right there. Oops. I want to make it black, like everything else. Black, okay. The oxygen, this oxygen is right here. It still has a proton on it. Oops, we haven't been doing that. That oxygen is positively charged. Now all we're going to do is remove the proton, and when we do that, we end up with our final product, okay, our hemiacetal. It's that simple. protonate the carbonyl, we activate it, we protonate the carbonyl, activate it, make it a good electrophile. There we go. We look over and we see that we have a nucleophile on the same molecule. So we just go ahead and do this nucleophilic attack at the electrophile, and when we do that, we form a ring. Here's our ring, right? And when we think about it, this carbon is right here. We've broken that double bond, so it's a single bond OH. There's a methyl group. That methyl group finds itself right there, okay? Then the final step is just the removal of that proton, H+. So the other product of this reaction is H+. So we see that we started with H+, we finished with H+. It's a catalyst. Now what I'm going to do is the next reaction is to show the mechanism for the formation of the acetal shown below under acidic conditions. And in fact, we can do the same thing because we're going to start off with our hemiacetal here. We can do the same series of reactions and get to the hemiacetal, and then all we're going to have to do is replace the OH group with this ethoxyl group. So let's go ahead and let's draw the hemiacetal from this, because it's the same starting material. Notice that we have the same starting material. 1, 2, 3, 4, 5, 6 carbons OH. 1, 2, 3, 4, 5, 6 carbons OH. So we can do the same thing. So now I am going to take a shortcut. The mechanism is exactly the same to get to this point where we have our OH and our methyl group. Oops. And there we go. Okay, it's a little messy, but there we go. So, and we had an H+ as our product. So now all we're going to do is go ahead and protonate our water. I'm sorry, our OH group, and we have this can just leave. We're going to break this carbon oxygen bond, and when we break it, the electrons are going to go up onto the oxygen, and water is going to leave as water, and we're going to get a carbocation that looks like this. That's our methyl group, and we have a carbocation, and I'm just going to put my water over here. Now we have to remember, so water could attack that carbocation, and the lone pair of electrons could just react there. We have a good electrophile, so let's do our conventional electrophiles are blue. Okay, water could be a nucleophile, and if we use water as a nucleophile, we're just going to go back where we came and all the way back to here perhaps. But we don't want to go that way. We want to go and somehow get to there. So we have to remember that we have ethanol around. So let's put a molecule of ethanol here. There's our molecule of ethanol, and that's going to be our nucleophile, so let's make it red like we like to make our nucleophiles. Okay, and we have a lone pair of electrons on there. and it's just going to be our nucleophile, and we're going to attack that electrophile. We're going to form a carbon-oxygen bond. There's our O, our H, that's our ethyl group, and we also have this methyl group, and I'm going to move it just so we can put a positive charge there. Now all we have to do is remove that. Let me positive charge. Green arrows are for moving electrons. And there's our final product. It's an acetal. Okay? So what you need to recognize is that when you go from a ketone to an acetal, there's a hemiacetal intermediate. So I just used that hemiacetal intermediate. Why repeat it? There. Okay, so we'll take a look at number 6 next.